Autoionization is when two identical molecules undergo an acid-base reaction. For water, that would look something like this. Two identical water molecules reacting with each other, one of them as the acid and the other as the base. If one of these water molecules is the base, that means that it is accepting an H plus ion, so it's being converted from H2O to H3O plus. And if our other water molecule is the acid, that means it's donating an H plus ion, so that means it's being converted from H2O to OH minus. So this is the products, these are the products of the autoionization of water. Let's rewrite this chemical equation so it looks more like what we're used to seeing. Instead of writing H2O plus H2O, let's write 2H2O, and let's include some states on this. Water is always in the liquid state. This is in equilibrium. The products are H3O plus in water, so this is aqueous, and OH minus, which is aqueous. Because this is an equilibrium reaction, we can write an equilibrium expression. Remember, equilibrium expressions are written as products over reactants raised to the stoichiometric coefficients, leaving out liquids and solids. Our products are the H3O plus and OH minus. They each have a stoichiometric coefficient of 1. So that means we don't have any exponents over here, or the exponent is 1, however you want to think about it. Our reactants, the water molecules, they are both liquids, which means that they are left out of the equilibrium expression. So we don't have any terms to write on the bottom of this fraction. Because this applies to the autoionization of water, the equilibrium constant K is given the subscript W to represent water. So we refer to this as the KW, H3O plus times OH minus. This equilibrium expression is sometimes referred to as the ion product of water. The value of the equilibrium constant Kw is super important. We use it a lot in chemistry. It is 1 times 10 to the minus 14, and it's definitely a constant that you should learn. Although you use it so much in chemistry that you don't really have to put a lot of effort into memorizing it, you'll just use it so often that you just automatically learn it. Now, when we have a solution of water, or not a solution, when we have a sample of water that is completely pure, so it has been distilled, there are no minerals present, there's nothing else present except for just water. In that situation, the stoichiometry for this reaction is such that there is 1 H3O plus ion for every 1 OH minus ion. This just comes from the stoichiometry of this equation. So when we have pure distilled water, the amount of H3O plus that we have present in that pure water is going to be exactly equal to the amount of hydroxide ion, OH minus, in that water. And since Kw is 1 times 10 to the minus 14, we can actually solve for the actual concentrations of H3O plus and OH minus in this pure water, 1 times 10 to the minus 7. If you're wondering exactly where did this 1 times 10 to the minus 7 come from, it came from the equilibrium expression. Kw is H3O plus times OH minus, and I know that Kw is 1 times 10 to the minus 14. And I know that H3O plus and OH minus are equal to each other, so I'm just going to call them x squared. And then if I solve for x, I get 1 times 10 to the minus 7. So that's where that came from. Let's just kind of scoot this out of the way right here. When we have this pure distilled water with the H3O plus and the OH minus concentration equal to 1 times 10 to the minus 7, we refer to this solution or this situation as neutral. So this is what it means for a solution or a sample of water to be neutral. A H3O plus equal to the OH minus, which is equal to 1 times 10 to the minus 7. If you're familiar with the term pH neutral, this is technically what that means. Now, the H3O plus and OH minus concentrations are not always equal to each other. In fact, this is a pretty rare scenario. Usually, one of these is greater than the other. So let's say, what if we have an H3O plus concentration that is greater than the OH minus concentration? So this would be in a sample of water that is not pure. It's got some other substance added to it. When the H3O plus concentration is greater than the OH minus concentration, this solution is what we refer to as acidic. So you might be taught to think about acidic in terms of what is the actual value of the pH or something along those lines, but this is actually the genuine scientific definition of what it means for a solution to be acidic. The H3O plus concentration is greater than the OH minus concentration. And the opposite scenario, where the H3O plus concentration is less than the OH minus concentration, in this situation, the solution is referred to as basic.